Hey everybody, welcome back. We're getting into the bulk of the chapter, which is 5.2 and 5.3. The reason why we did all that reciprocal stuff is that we can introduce you to vertical and horizontal asymptotes. That'll be something that'll be very important in this section here as well. So this is the main part of the chapter. So what I want to do is just a quick overview of what we did in the first section. If you remember, if we have a reciprocal of y is equal to 1 over 2x minus 5, and how is that related to the original function that we have? Well, one thing that we do know is that we have a vertical asymptote anywhere there's an x-intercept. Whoops. Something like that. We have a horizontal asymptote along the x-axis. And from there, what we're going to do is we're going to look at what section of the graph our original function is in. So if I was to label them 1, 2, 3, and 4, I see that our original function is in 2 and 3. So our reciprocal should also be in section 2 and 3. So if I was to graph what it would look like in section 2 and 3, there's only one way that it could look, and it would be like this and like this. It's got to approach that vertical asymptote either from the top or the bottom. And on the very far right and left side, it's got to go along that horizontal asymptote. Same goes for our quadratic that we have over here. So if we have the original function here of y is equal to x squared minus 3, and that one's graphed on here, we have the reciprocal up top. It's just been factored at the bottom, but it's the same. One thing that we do know is that we're going to have vertical asymptotes wherever the x-intercepts are. In this case, it's going to be at 0 and at 3. We're going to have a horizontal asymptote right along the x-axis. That's always true for reciprocals. And now we've broken our graph into 1, 2, 3, 4, 5, and 6. So I know my graph is in 1, so my reciprocal is going to be there. It's in 4, and it's also in 5. So my reciprocals are going to be in 1, 4, and 5 as well. So if my graph is in 1, I know that it has to come along the horizontal asymptote and go up. If my graph is in the middle here, we know that it has a minimum, which looks to be somewhere around negative, I would say 2.25. So its reciprocal would be 1 over negative 2.25, which is just about half almost. So put it about half. So I know my graph must come up, touch here, and come down. It's got to be in the same section of the graph, so that's why it's going to be on the bottom. And then finally, it's going to be up in the top right-hand corner. So the only possibility is that it looks something like that. And that's how we end up making a sketch of the reciprocal of that original function up top. That being said, what we're going to do is we're going to be graphing rational functions. Now, what rational functions are is a fraction like the reciprocals. However, there's a polynomial on top and on the bottom. So there's some characteristics that we're going to have to pay attention to, and those are the ones that are listed below. So rational functions could have a hole in the graph. Now, you did some of this back in grade 11, but a hole in the graph is created whenever you have a factor that can be canceled out. So if you have some value on top and bottom that can be canceled out, so in this case like r of a. So if I look at our original function that we have here, I notice that we can cancel out x plus 2. So that means we would have a hole at x is equal to negative 2. Right, the x value that's created by that factor. How about vertical asymptotes? Vertical asymptotes happen where the denominator is equal to 0. So once I've canceled things out, we see what's left over. So for this case, if I cancel out these two here, I see we're going to have x minus 3 and x minus 4 on the bottom. We've canceled them out. Can't do anything else. Is there any x values that make this undefined? Yes, that will happen when x is equal to 4 because that will make the bottom equal to 0. So you can even write out and say, well, x minus 4 is equal to 0, solve that through, and you find out that we have a VA, vertical asymptote, at x is equal to 4. So that graph is going to have a hole in the graph at -2, and it's going to have a vertical asymptote at 4. So when we talk about this hole that the graph could have, well, that just means that where x is equal to -2, so 1, 2 over here, no matter what the graph looks like, so it might be something like this coming up, around, when it gets to -2, it means it's going to have an open dot, and it's going to continue on. We don't know the y value. I can get the y value by substituting in -2 into the graph to find out where that hole would actually be, but that's how the hole works. Vertical asymptote, once we've simplified it through, we found out the value of x that would make the bottom, the denominator, 0. These two here might be new to us. Horizontal asymptotes, we kind of talked about those for reciprocals, but reciprocals were always 1 over some value x plus 3. What happens if we have a polynomial on top? And that's what we're going to look at here. So for this one, it says horizontal asymptotes occur when the numerator has a degree equal to or less than the denominator. So the numerator is equal to or less than the denominator in terms of its degree. It says if the degree of the numerator is less than the denominator, the horizontal asymptote will always be at 0, and that was the case for all reciprocals. So when I had that 1 over x plus 3, if I looked at that, the degree of the top was 0, degree of the bottom was 1, which meant the denominator had a bigger degree, and that was the case of all the ones we looked at yesterday. So the horizontal asymptote was always at 0, but it's not always at 0. If the degree of the numerator and denominator are equal, the horizontal asymptote will be at the quotient, the division, of the leading coefficients of the numerator and denominator. So that means we just take those beginning numbers that we have and divide them if possible. So let's look at this first one we have here. Degree is 1, so the same degree. So what we're going to do is we're going to take the leading coefficients and divide them. 3 divided by 2. That means we're going to have a horizontal asymptote at y is equal to 3 over 2, or 1.5. So it's not going to be at 0, it's going to be 1.5 above. 1.5 above is where I draw that horizontal line. This one here, top has a degree of 1, bottom has a degree of 2, so the bottom has a bigger degree. When the bottom has a bigger degree, that means we have a horizontal asymptote at 0. Third one, same idea. Degree on top is 0. Degree on the bottom is 3. So degree on the bottom, denominator is higher. So we're going to have a horizontal asymptote again at 0. Those are supposed to be at signs. It kind of looks funny. And finally, the last one that we have over here. When we have a degree of 2 and degree of 2, same degree, we're going to divide those leading coefficients. 8 divided by 2, which is 4. So that means we're going to have a horizontal asymptote at y is equal to 4. So that means 4 above, we're going to have that horizontal line. So are we always going to have a horizontal line? Well, if the degree is the same or denominator is higher, yes, we will. Then what is this thing? So oblique or slant asymptotes. So sometimes we can have an asymptote that is not a horizontal line. It could have some slant to it, like a regular line that we've drawn. We're either going to have one or the other. We're not going to have both. You can't have a horizontal and an oblique asymptote. It's one or the other, because there are differing circumstances when they happen. So oblique asymptote happens when the degree of the numerator, the top, is exactly 1 degree greater than the denominator. So in this case that we have here, the degree on top is 2, degree on the bottom is 1, so the numerator is 1 more. Over here, the degree on the top is 2, degree on the bottom is 1. So same situation. So these ones are not going to be a horizontal line. What they're going to be is a slanted line. So if I imagine what this looks like, I might have some vertical asymptotes, maybe one here and one here, But instead of being a horizontal line, you might have something that looks like this, that our line will approach. And if that was the case, you might have some, your graph might end up looking something like that, or like that. So it's not approaching a horizontal line. It could get close to a slanted line, as x is really, really big or x is really, really small. It could cross it in the middle, but as x gets really, really big or really, really small, it doesn't have to be a horizontal line. So that being said, how do we find the equation of that line? Well, we've learned that when we have something like this, we can divide them. If you divide them, that's going to give you the equation of the oblique asymptote. So that's a linear equation on the bottom. We could use our synthetic division that we spent time on. We could have a -1 out front, 2, 0 as the placeholder for x, and -3. And if you remember synthetic division, we would have a remainder over here. For oblique asymptotes, we don't pay attention to the remainder. What we're interested in is these values here, which means that our oblique asymptote in this case would be at y is equal to 2x minus 2. So it wouldn't be at y is equal to 0, y is equal to 4. It's a line that has some slant to it. Same goes for the one over here on the right. If I wanted the equation of the oblique asymptote, I would divide. If I was to use synthetic division, 1, 2, and there's no constant, so I'll put 0 as its placeholder, 2, -2, 0. And in this case, we have 0 remainder, but our equation is y is equal to 1x plus 0, or just y is equal to x. That's the equation of our oblique asymptote, so I would draw that. As x got really big or really small, our function would get close to that slanted line, if that was the case. So you're going to have one or the other, one either horizontal or oblique asymptotes, but you're never going to have both. So one quick overview before we do some examples. Rational functions and the restrictions that they have. If you can cancel out a factor, x minus a, well, what's created in that case? We have a hole in the graph. If there is a value a that causes the denominator to be 0, after we've canceled out all of our holes if they exist, there is a VA, vertical asymptote, at x is equal to a. If the degree of the denominator is equal to or larger, so that means the bottom is equal to or bigger than the top, then there is a horizontal asymptote. There's two cases. So it says if the degree of the numerator is the same, so if the degree on top and bottom is the same, then horizontal asymptote is equal to the quotient or the division of the numerator and denominator's leading coefficients. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is always at 0, or y is equal to 0. And finally, if the degree of the numerator is 1 more than the degree of the denominator, then there is an oblique asymptote, or slope asymptote. To find the equation, divide the numerator and the denominator, and the quotient is the equation of the oblique asymptote line. Disregard the remainder, because we're just interested in that polynomial that's created. That's our oblique asymptote. And finally, a rational function cannot have both. So from here, there's some examples below